Namaskaram. Today we will discuss the divergence theorem and its application to find flux of a closed surface. These are the solutions of previous homework. Divergence theorem is used to find flux of a vector field through a closed surface. And it is clear that a closed surface has two orientation. One is outward orientation and other is inward orientation. For example, you consider this cube. Okay, here sigma stands for the union of these six faces. Okay, not only this face, here sigma stands for the union of the six faces of this cube. And it is clear that this surface has two orientation. One is outward orientation like this, other one is inward orientation. Similarly, this is a cylinder and top and bottom covered by two circular regions. And this is a closed surface, including this is a union of these three surfaces: top, lateral, and bottom. And this is also a closed surface, and it has two orientation. One is outward orientation like this, and other is inward orientation. Okay, so that is the idea of outward and inward orientation of a closed surface. Okay, we know that what is divergence. Divergence of a vector field fx, y, z is equal to fi plus gj plus hk is defined like this, and it is denoted by div f. Okay, dou f by dou x plus dou g by dou y plus dou h by dou z. And this is our main result in this session, Gauss divergence theorem. Let G be a solid whose surface sigma is oriented outward. This is important. We consider the outward orientation of a surface. Sigma is a closed surface, isn't it? Because sigma is the surface of a solid, so it's a closed surface. If fxy is equal to fi plus gj plus hk, and n is the outward unit normal on sigma, then this is our surface integral, double integral over sigma f dot n ds. This is our surface integral. We can evaluate this surface integral using this triple integral. This is our normal triple integral over g div f dv. Okay, and important thing is this sigma should be a closed surface, because this sigma is bounded by a solid, so it is always closed. Okay, so this is the main result, and using this result we can easily evaluate surface integrals using triple integrals if the sigma is a closed surface. Okay, first problem. Use divergence theorem to find the outward flux of the vector field f equal to zk across the sphere x square plus y square plus z square equal to a square. We know that this is a sphere of radius a with the center origin. Okay, so what is our sigma? What is our surface sigma? It is clear that sigma is the spherical surface. Okay, and what about capital G? G is the region that encloses this sigma. You got it? So the outer surface is sigma, and the inside of the surface sigma is our G, the volume enclosed by sigma. Okay, so we can easily evaluate the flux using divergence theorem because the sigma is a closed surface. What is the formula of flux? The flux is equal to double integral over sigma f dot n ds. This is the basic formula of flux. By Gauss divergence theorem, we can evaluate this surface integral using this triple integral over g div f dv. And what about div f? Okay, here capital small f equal to 0 because 0 plus 0 j plus zk. So g is also 0, h is equal to z. So div f becomes 0 plus 0, 0 plus 0 plus derivative of h with respect to z, that is 1. So div f equal to 1. Substituting this div f here, so this becomes triple integral over g 1 dv. Then what about this triple integral? Is it familiar? Yes, triple integral over a solid 1 dv gives the volume of g. Okay, we know what is our g. G is the sphere with the radius a. So what is the volume of a sphere? That is equal to 4 by 3 pi a cube, because here radius is a. So the total flux is equal to 4 by 3 pi a cube. Okay. Yes, 4 pi a cube by 3. Okay, second problem. Use divergence theorem to find the outward flux of the vector field, this one. f equal to 2xi plus 3yj plus z square k across this unit cube. Here unit cube means all the sides are 1 unit. Okay. So what is our sigma? So first of all we have to identify sigma and g. What is our sigma? Sigma denote the outward oriented surface of this cube. Okay, outward oriented surface of this cube is sigma. And what about g? G is the region enclosed by the surface sigma. Okay, that is our unit cube. So now it is clear what is sigma and what is g. Okay, then we can easily evaluate the flux using Gauss divergence theorem. Phi is equal to the surface integral, and by Gauss divergence theorem this is equal to this triple integral. And what is div f? Here this is our small f and g and h. So the first term is dou f by dou x, that is 2, plus dou g by dou y, that is 3, plus dou h by dou z, that is 2z. Okay, so this is our div f and dv. This is 2 plus 3 is 5, so this becomes triple integral over g, 5 plus 2 is a dv. Next we have to evaluate, the next we have to integrate this function over this solid g. So it is clear that from this, on this solid g, what is the range of x, what is the range of y, and what about the range of z? It is clear that x is varying from 0 to 1, isn't it? X is varying 0 to 1, and what about y is also varying from 0 to 1, and similarly z is also varying from 0 to 1. So we can easily set up this triple integral as like this: 0 to 1, 0 to 1, 0 to 1, 5 plus 2 z dx dy dz. Okay, now you can easily evaluate this. First you integrate with respect to x, then y, then z. First we integrate with respect to x. So 5 plus 2z is a constant. We can treat this is a constant because integration is with respect to x. So this become 5 plus 2z into x, and limit is 0 to 1. Okay, so after substituting this upper limit and lower limit, this term become 1. So this is again 5 plus 2z. Okay. Okay, so this become 5 plus 2z. Next we have to integrate this with respect to y. As similar to the first case, 5 plus 2 is again a constant with respect to y. So this become y 0 to 1, and upon substitution this become 1. So again integrand is 5 plus 2z. Next we have to integrate with respect to z. So this become 5z plus 2z square by 2, that is nothing z. Okay, so limit is 0 and 1. So whenever z equal to 1, this becomes 6. Whenever z equal to 0, this time is 0. So final answer is 6. So this is our total flux, 6. Okay. Okay, next problem. Use divergence theorem to find the outward flux of the vector field x cube y plus y cube j plus z square k across the surface of the region that is enclosed by the circular cylinder x square plus y square equal to 9. We know that x square plus y square equal to 9 is a circle in 2D, but in 3D it's a cylinder. Okay, and the planes z equal to 0, that means this bottom surface, and z equal to this top surface. So this is the cylinder, a closed cylinder. Sigma is the surface of the cylinder, and the region bounded by the sigma is our g. Okay, so how to find flux? Okay, this is the formula. And what about div f? That is 3x square plus 3y square plus 2z dv. Okay. Okay, then how to evaluate this triple integral? Because here we have to integrate over a cylindrical shape. So better we use cylindrical coordinates instead of Cartesian coordinates. Okay, what is our cylindrical coordinates? In cylindrical coordinates, x is equal to r cos theta, and y is equal to r sin theta, and z itself. Okay, there is no change in z. Okay, so upon simplification, what happened? This term become 3 times r square, because 3 times x square plus y square, x square plus y square is r square. This is remains 2z. Okay, and what about our dv? dv become r dz dr d theta. This part is same as polar coordinates r dr d theta, and dz is there. So this is the part corresponding to dv. So this integral become, so this is the integral. Next we have to set up the limits of z, r and theta. Okay, it is clear that z is varying from 0 to 2. Okay, So Z is varying from 0 to 2. And what about R and theta? We have to cover this entire region. So R should varying from this point to this boundary. Okay. And what about this equation of the circle? The equation of circle, the boundary equation of this cylinder or equation of this base circle is x square plus y square equal to 9. That is 3 square. So this radius is 3. Okay, so R should varying from 0 to 3. So this is the range of R. R should varying from 0 to 3. And again, we have to cover this entire solid. To cover this entire solid, our theta should varying from 0 to 2 pi. So this is 0 to 2 pi. So this is the full setup of this integral in cylindrical coordinates. So first we have to integrate with respect to z. So we can treat this 3r square plus 2r, sorry, 3r cube plus 2r is a constant. So this become like this, and we have to substitute 2 and 0 for z. After substituting this upper limit and lower limit, this expression become 6r cube plus 4r dr d theta. So next we have to integrate with respect to r. Okay, this become r raised to 4 by 4. By simplifying, we cancel 1 2. So this become 3 by 2 r raised to 4. And this is r square by 2. So by cancelling it 2, this become 2r square. And these are the limits. Upon simplifying our substituting upper limit and lower limit, this expression become 279 by 2 d theta. Next we have to integrate with respect to theta. So this become 279 by 2 theta, and the limits are 0 to 2 pi. So this become 279 by 2 into 2 pi, isn't it? So after simplification, this become 279 pi. 279 pi. This is the total flux. Next problem, we have to find the flux of this vector field x cube I plus y cube j plus z cube k across the surface of the region that is enclosed by the hemisphere, that is z is equal to square root of a square minus x square minus y square. So this is the upper part of the hemisphere, because here z is positive square root, so z is always positive, so upper portion. Okay, and the plane z equal to 0, the bounded below by the plane z equal to 0. So this is the solid G and its surface is sigma. Okay, then we know how to evaluate the flux using divergence theorem. Phi is equal to this is, and this is equal to divergence. And what about divergence? That is 3x square plus 3y square plus 3z square. This is our divergence. Then how to evaluate this triple integral? Because we have to integrate over G. What is G? G is the solid hemisphere. Okay, that is G. So since it is a our surface, our solid is part of a sphere, better we use spherical coordinates. Okay, to compute this triple integral, better we consider spherical coordinates. That is easy. So what are the spherical coordinates? Okay, this is our spherical coordinates. X equal to rho sine phi cos theta, y is equal to rho sine phi sine theta, and z is equal to rho cos phi. And what is rho? Rho is nothing. Rho is the distance between origin and the point, that is rho. And what is phi? Phi is the angle. Suppose this is the point, then suppose this is the point, then what is phi? Phi is this angle. This angle is phi. Angle between positive z axis and that vector, that is phi. Okay. And what is theta? Theta is measured on this plane, xy plane. You take the projection and angle between positive x-axis, that is theta. Okay, so these are the three parameters. So in this case, what about theta? In this case, what about rho? Rho should varying from 0 to this radius, and we know that radius of the sphere is a. Okay, so we have to set up this integral, and the rho should varying from 0 to a, because 0 to this point, this radius, that is 0 to a. And what about next one, phi? Phi is the angle between positive z axis and this vector. So here the maximum change of phi is from positive z axis up to this xy plane, whatever the direction up to xy plane, to this angle is maximum pi by 2. The full angle is pi. Okay. The maximum change of phi is only pi. Whatever be the direction, the angle is maximum pi. So this is pi by 2, 0 to this point, that is 0 to pi by 2. So 0 to pi by 2, this is the change of phi. Next on theta. To cover this entire solid, theta should varying from 0 to 2 pi. So 0 to 2 pi. So this is the setup, this is the main concept of this integral. Then what happened? And what about rho? Again one more inequality. What about rho square? Rho square is equal to x square plus y square plus z square. Okay, so here 3 is common, you can take outside. So this become 3 into x square plus y square plus z square, that is 3 rho square. Okay, what about dv? In the case of cylindrical coordinates, not cylindrical, in the spherical coordinates. In the case of spherical coordinates, our dv become rho square sine square phi d rho d phi d theta. So this is our dv rho square. Oh, sorry, this is not sine square. This is only sine. Sorry, only sine. So rho square sine phi d rho d phi d theta. This is dv in spherical coordinates. Okay. Now this 3 is a constant. You can take outside. So 3 times. And this is rho raised to 4. The integral of rho raised to 4 is rho raised to 5 by 5. And sine theta is a constant. 0 to a. Then by substituting a and 0 for rho, then we get 3 a raised to 5 by 5, 0 to 2 pi, 0 to pi by 2, sine phi d phi d theta. Okay, when we substituting rho equal to a, this become a raised to 5, a raised to 5 by 5. Okay, when rho equals 0, this time is 0. Okay, and a raised to 5 is a constant, that's why we take outside. Here. Next we have to integrate with respect to phi. The integral of sin phi is minus cos phi. And what about cos pi by 2? Cos pi by 2 is 0 and cos 0 1. Upon simplification, we get this become 1. So integral is like this. Then next we have to integrate with respect to theta. So this is 3 a raised to 5 by 5 theta 0 to 2 pi. This become 2 pi. So upon simplification, this become 6. This is actually 2 pi. 2 pi into 3, that is 6 pi. 6 pi a raised to 5 by. Okay, so this is the total flux. 6 pi a raised to 5 by 5. Clear? This is your homework. Thank you.